In this unit on work, energy, and power, we've talked about work and we've talked about power, and now it's time to talk about energy. And this lesson is the last lesson before your mid-unit review and your mid-unit test. So keep that in mind as we work through this lesson that you've got a test coming up. So lesson 4, types of energy. In general, a force in the direction of motion, like force 1, F1 below, does positive work. So F1, positive work because it's in the same direction as the motion. And a force opposite to the motion, like F2, let's try a different color, F2 is in the opposite direction of the motion, does negative work. So although work can be positive or negative, we know it's not a vector, it doesn't have a direction, but it does consider whether it's in a certain direction, the force is in the same direction as motion or opposite the direction of motion. So then what does negative work actually mean? And that requires us to talk about energy. So energy itself is actually defined in terms of work, and it is the ability to do work, the ability to move something over a distance using a force, because work we know is force times distance. So work, again, force times distance. If energy is the ability to do work, energy is the ability to exert a force over a distance. And there are many different types of energy. We're going to focus on 2 main ones, but we're going to take an overview first. So the energy of motion is called kinetic energy, and any object that is moving automatically has this kind of energy. Heat is also a form of energy, and it's often created by friction, although not always. We could create heat using a fire as well. We get lots of heat from things rubbing together in terms of friction. Gravitational potential energy. This is the energy due to an object's height above the ground. And if you think about this in terms of force and distance, when something hits the ground, then it's going to exert a force traveling through a distance. Or actually, it's the force of gravity that pulls it down, making it go through a distance. Anyway, gravitational potential energy has to do with height, how high above the ground you are. And then there are different forms of chemical potential energy, for example, gunpowder, or you're releasing the chemical potential energy in wood when you're burning a fire, or from gas or natural gas, from petrol when you're running a car. Those are all kinds of chemical potential energy that you're releasing to do something else with it. And of course, there are other forms of energy, like sound is a form of energy, elastic energy. When you stretch an elastic band, you're putting a force on it through a distance. For example, the energy stored in a rubber band. Nuclear energy is stored within the nucleus of an atom, so there are lots of different kinds of energy. And in this course, we are going to focus in on what we call mechanical energy. And mechanical energy comes from 2 main types, and that is kinetic energy due to motion, and it is gravitational potential energy due to an object's height. So we're not going to look at all potential energy. We saw there were quite a few different kinds of potential energy. We're going to look specifically at gravitational potential energy. And it's actually pretty straightforward. So that's due to height above the earth. And okay, so let's go back to, well, what do we say? Well, what does negative work mean? When you do negative work, what this really means is the object is losing energy. So you're taking energy away from the object. When you do positive work, you're giving the object energy. So when you push something to make it go faster, you're giving it more kinetic energy. And when you push against it to make it slow down, you're making it lose energy. You're taking away, you're doing negative work. When you lift something higher above the ground, you're doing positive work because you're giving it gravitational potential energy. And when you let something drop, it is losing its gravitational potential energy, and at least initially it's gaining kinetic energy as it starts to move, but when it hits the ground, it actually loses all that energy as it comes to a stop. So at this point, we're actually going to take a quick break from the lesson notes to watch a video on how work and power work. So here it comes.
In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock. When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt, who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse. This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They are adding energy to the clock at a rate of 2.5 watts. You'd need about 40 times as much to run a bright 100-watt light bulb. Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find an answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.
So hopefully that video gave you a better appreciation of the connections between work and power that we've talked about already, and energy, what we're looking at right now. So the first kind of energy we're going to focus in on is potential energy. And in this course, 95% of the time when we say potential energy, we mean gravitational potential energy. But there are a few exceptions to that, and one is the following. So potential energy is stored energy. In the case of gravitational potential energy, I'm storing energy by lifting something and holding it above the ground. When I'm stretching a rubber band, I'm storing the energy in the stretch. So for example, here's a picture of somebody pulling back on a bow, and it says, suppose it takes 250 newtons of force to pull the arrow back 0.78 meters. And this would be considered an average force, because if you've ever pulled back on a bow, you know it's really hard to get it going at the beginning, and it gets easier as you pull out. So to properly analyze this whole situation, we would need a graph of force versus distance. So we're just going to say this is the average force that it takes 250 newtons to pull the arrow back 0.78 meters. So it used to be here, the back of the arrow moves back 0.78 meters. How many joules of energy are stored in the bow? Well, the answer to that question is really just how much work did we do, because the work that we did is the energy that was stored. So we can answer this pretty quickly. We go, okay, well, the work that we did was force times distance. I'm given the force of 250 newtons times a distance of 0.78 meters. Pull out my calculator, and my calculator tells me that's 195. And in this case, we know that work is measured in joules, and it turns out, as I said in the video, that energy is also measured in joules. So I did 195 joules of work to stretch this back, and that means I've stored 195 joules of energy. So the next part asks, when the string is released, what happens to this stored energy? And the answer to that is, well, when you release the string, the arrow goes flying, and it turns into the kinetic energy of the arrow. So the energy that we stored in the bow by pulling it back is transferred to the arrow, and that's what makes it move, which is called kinetic energy. Just for fun, we're going to take another short break and watch a video of a girl in a human slingshot so you can see the stored energy released in real time.
All right, have fun.
1, 2, 3.
So when you stretch a rubber band back, you are storing potential energy, the same way the potential energy was stored in the slingshot when they pulled it back. A battery has stored electric potential energy. However, in this unit, as we said before, we are going to look at one specific type of potential energy called gravitational potential energy. And this is the work that you do against gravity in order to change an object's height. And the equation for this is your potential energy is equal to the mass times your acceleration due to gravity times the height of the object. And you may recognize this as being the work done against gravity to lift something up, except usually we use D for distance just because work equals force times distance. In this case, we're talking about height of the object above the ground. So you can really interchange the two. So mgh or mgd, h is height. Or if we know that the weight, remember that weight is measured in newtons, it's not the same as mass or the force of gravity, then your equation would be the force of gravity times the height of the object. That would also be a valid equation. So, for example, Jaden has a mass of 75 kilograms. What is his weight? So this is just reminding you again, weight is measured in newtons. It's not the same as mass. So to find his weight, I'm going to do Fg equals mg. His mass is 75. His g on the earth, we're assuming he's on the earth, is 9.8. Pull out your calculator. And my calculator tells me I have a weight or a force of gravity of 735 newtons. So again, just reminding you, weight is Fg, is not the same as mass, and it's measured in newtons. So part B, when Jaden jumps, he can raise his center of mass 75 centimeters from the ground. At the top of his jump, how much potential energy does he possess? And where did that energy come from? So we already have Fg, so we can skip right to this PE equals FGH. If you wanted to calculate again, you could do MGH, but since we have this 70-35 already, I'm going to make use of it. And I didn't round it at all, so I don't have to worry about rounding errors. And height, he's going 75 centimeters above the ground, so 75 centimeters, convert that into base units. It's 100 centimeters in 1 meter, or you can do 10 to the 2, and divide by 100 is 0.75 meters. That's the number I'm going to plug in for height. He can actually jump pretty high. 75 centimeters is a fair distance. So again, pull out your calculator and plug that in. And it tells me that his potential energy is going to be 551.25. And I'm going to round that to 3 sig figs. Again, remember 2 or 3 sig figs is fine, so 550 or 551. And potential energy is measured the same as work in joules. That would be my final answer. Okie dokie. Another example. How much gravitational potential energy? Oh, sorry, I missed the second part of part B. Where does that energy come from? The energy for him to jump, the energy comes from the food that he ate for breakfast. Whoops. So it comes from the food that he ate, and then that is stored as chemical potential energy in his muscles and then released as kinetic energy to get him shooting upward. So where does the energy come from? The food that he ate. Sorry, now we're moving on to example 3. How much gravitational potential energy does an object have if it is on the ground? Well, if it is on the ground, and I know that my potential energy is mgh on the ground, that would mean h equals 0, so that must mean it has no potential energy. Potential energy is also 0 joules. Not really necessary to do any calculations, just remember if you're on the ground, your height is going to be 0. So that's gravitational potential energy, and it's pretty much the same thing as the work done to raise the object to that height. Now we're going to look at kinetic energy. And kinetic energy is the energy of motion. So how fast are you moving? And this equation for kinetic energy also depends on mass, but it's not quite as straightforward as your gravitational potential energy. Your equation for this is going to be 1/2 times mass times velocity squared. So this time we don't care about whether we're on the Earth or where, because I'm not using g at any point, but I still do care about the mass of the object and how fast that it's moving. And you'll notice that the mass is, it's proportional to the mass, so the more mass you have, the more kinetic energy you're going to have, but it's proportional to velocity squared, meaning the faster you go, the really much more kinetic energy you're going to have, because every increase is going to be squared. So, for example, a .357 Magnum bullet weighs 8.1 grams and travels at 490 meters per second. How much kinetic energy does it possess? So I gotta watch out, this 8.1 grams is not in base units, so I've got to convert that. So it's gonna be 10 to the 3 grams in 1 kilogram. And that means divide by 1,000, or 1, 2, 3 zeros, and then 1 kilograms. So not a very big mass for a bullet, but it's going to end up with a lot of kinetic energy because we're squaring the velocity. So my kinetic energy is 1/2 times this very small mass that I found times my velocity squared. So let's pull out your calculators and figure that one out. So even with such a small mass, I still end up with a fair amount of energy at 972.405. I'm going to round that to 3 sig figs, so 972 joules. Energy always measured in joules. Doesn't matter if it's potential or kinetic. All right, example number 5. A car has a mass of 1,000 kilograms. How much kinetic energy is required to reach a speed of 5 meters per second? In other words, it's asking basically how much kinetic energy does it have when it's going at 5 meters per second, because we know that to reach that speed, starting from rest, it would have 0 kinetic energy to start with if it starts from rest. So why don't you pause your video and see if you can figure out example 5A on your own, and then come back and double check. So it turns out the car has a kinetic energy of 12,500 joules. So a car going quite slow, 5 meters per second, has a lot more energy than the bullet going speeding fast, and can do a lot more damage to a brick wall than one teeny tiny bullet would do. Let's take a look. Part B then asks how much kinetic energy is required to reach a speed of 10 meters per second. So let's go through all those same calculations again. It's still going to be kinetic energy is 1/2 times 1,000, but this time instead of just 5 meters per second, we're going at 10. Plug that into your calculator and see what you get. Turns out it's going to take 50,000 joules to reach a speed of 10 meters per second. Now, to reach a speed of 5 meters per second, 125 or 12500, this is 50,000. This is actually 4 times as much as the 5 meters per second. Not just twice as much, speed was twice as much, but it took 4 times as much energy because of the velocity squared. So twice the speed squared is 4 times as much energy as the 5 meters per second. Now how about for 15 meters per second? Well, if we plug in that information as well, 1/2 times 1,000 times 15 squared, what's that going to end us up with? Let's see, 0.5 times 1,000 times 15 gives us, look at that, 112500 joules. And if I was going to write this as a final answer, I would have to round this to 2 or 3 sig figs, but what I'm trying to emphasize here, from 5 to 15, this is 3 times as much, but it's actually 9 times as much energy because of that velocity squared factor. So 3 times as much speed requires 9 times as much energy, because 3 squared is 9. Just keep that in mind. The faster you go, the energy keeps going up way faster than just double or triple. So using that, it says suppose an object has a kinetic energy of 5,000 joules, so this is the original kinetic energy. How much kinetic energy is required to double its speed? So double means times 2, twice the speed, but because we're squaring that, it's going to take 4 times the energy, which is going to be then 4 times 5,000 is 20,000 joules of energy. How much kinetic energy is required to triple its speed? Well, that's going to be 3 times its speed, means 3 squared, 9 times the energy, which turns out to be 9 times 5 is 45,000 joules. So again, going up a whole lot faster, and then quadruple would be 4 times its speed, 16 times the energy. 16 times 5 is going to be, I believe it's 80,000. Well, let me just double check that. I'm doubting myself. 16 times 5,000, it is 80,000 joules. So the faster you go, the more energy that is required at a x squared, speed squared rate. So this idea of double the speed, double squared, or 4 times the energy explains why sports equipment like golf clubs, tennis rackets, and hockey sticks have become lighter, not heavier. This allows you to make them move faster and give them more energy. In golf, for example, we talk about club head speed because that's where the majority of the mass is. And again, the faster you can get it to go, velocity squared is going to give you more kinetic energy. Whereas kinetic energy is only proportional to 1 times the mass. If you can get it going faster, it gets you farther than just increasing the mass. And that's also why it's more difficult to speed up once you already possess kinetic energy. It's relatively easy to increase your bike from 0 meters per second to 5 meters per second. From 5 meters per second, not very fast. It's tougher to go from 5 meters per second to 10 meters per second because it's requiring, again, lots more energy. It's even tougher to go from 10 to 15 meters per second, even though it's still only an increase of 5 meters per second. We saw that this was 4 times the energy of 5 meters per second. And this is 9 times the energy of 5 meters per second. So it requires a whole lot more energy to get there because of that velocity squared. And it also explains why the damage to occupants in car accidents is so dramatically increased, dramatically different between an accident at 20 kilometers per hour compared to an accident at 80 kilometers per hour. Again, velocity squared. The 80 kilometers per hour will experience 16 times more damage because it's 4 times as fast, 4 squared 16, and also takes 16 times more distance to stop, or 16 times more force to stop one with the other. Because, again, we're talking about work to make it stop, it's equal to force times distance. If it starts out with more energy, it's going to take way more force or way more distance in order to stop. All right, a few more examples. A 25 kilogram mass object has a kinetic energy of 924.5 joules. How fast is it traveling? So this is really just taking your kinetic energy equation and solving for velocity instead of for kinetic energy. Because we have kinetic energy to plug in, we have the mass to plug in, we need to solve for velocity. So in order to get the v by itself, first I'm going to move this 1/2 to the other side. And the way that I do that is I'm going to multiply both sides of my equation by 2. Because I know that 1/2 times 2 is going to be 1. In other words, half of 2 is 1, and what I do to one side, I'm going to do to the other. So this gets me 2 kinetic energy is equal to mv squared. Then in order to get the v squared by itself, I'm going to divide out the m, because it's m times v squared, so I'm going to divide it. So then I've got 2 kinetic energy over m equals v squared, and to finish it off, I'm going to take a square root of both sides. Now, we usually, when we take a square root, have a plus or minus in front of this, but unless you're interested in the direction of the velocity, we're not really going to care about the minus or plus, we're just going to take the magnitude. So in the end, we've got v equals square root of 2ke over m. And at this point, we can start plugging in our numbers, so twice the kinetic energy, so 924.5, divided by the mass of 25, pull that out, take out your calculator, and see what you get. The only thing I would say is when you're typing in something under a square root, make sure you've got your parentheses all in the right place so that you're square rooting the whole thing, or type it in first and then take the square root of the answer. But our final answer is 8.6 meters per second. And again, because there's no direction given in the question, we don't care. We're not going to do negative 8.6 or positive 8.6, just 8.6. All right, another example. A 350 kilogram roller coaster has a kinetic energy of 137,200,000 joules at the bottom of the first hill. How fast is it traveling? So how fast, that's asking velocity. So what's going on here is we've got a roller coaster that goes up and down hills, and at the bottom of this first hill, it's got kinetic energy of 137,200 joules. And we want to know how fast is it going. That is the question. So you can figure that out using the same equation from example number 7. So why don't you pause your video now and do that. So for part A, you should get 28 meters per second. Now, part B says if all this kinetic energy came from potential energy, how high is the first hill? In other words, at the top of the first hill, it had this as its potential energy, and it turned into kinetic energy as it went down the hill. So its potential energy at the top of the hill was 1372,000 joules. And I'm asking how high is the first hill? So we want to find out. We know that potential energy is mass times g times h, and we're trying to solve that for h. So divide both sides by mg, because it's multiplying the h is the mg, and that gives me then h equals pe over mg. Plug in your numbers. So potential energy is the 137,200 that we had for kinetic energy in part A. The mass is still 350, and the acceleration due to gravity is 9.8. Pull out your calculator, see what you get. Now when you type it into your calculator, you may just need to be careful to put parentheses around your denominator since you're wanting to divide by both of these things. And if you don't have parentheses around them, it will think that you're multiplying by the 9.8 instead of dividing by the 9.8. And that gives me a height of 40 meters. So my first hill had a height of 40.0 meters. Let's keep going. Example number 9. How high would we need to lift a 65 kilogram object to give it a potential energy of 15,288 joules? You should be able to do this one. Pause your video, try it on your own, then come back and see how you did. And it turns out you would need to give it a height of 24 meters. Pause your video if you need to write anything down, and we'll keep going. So suppose we want a 2,500 kilogram pile driver to hit the ground at 18 meters per second. What is a pile driver, you ask? The best way to figure things out is to Google them. So let's see what we get when we use Google Images. So Google tells us a pile driver is a device used to drive piles, which are big long posts, into soil to provide foundation support for building or other structures. And if you want to look at images, you can see all sorts of, these are what pile drivers are. So okay, back to your regularly scheduled physics. So we've got a pile driver that we want to hit the ground at 18 meters per second. So how much kinetic energy does it need? Okay, so we know kinetic energy, 1/2 mass times velocity squared, so 1/2 times the 2,500 times the 18 squared. See what that gets you. And my calculator tells me that's 405,000 joules. So let's write that down. 405,000 joules. So that's how much kinetic energy we're going to need. Now part B asks, if all of this kinetic energy comes from potential energy, how high do we need to raise it? In other words, if this is my potential energy, 405,000 joules, that's going to convert into this kinetic energy. We want to know what is the height. Well, from previous examples, we know that height is potential energy divided by mg. So we're going to take this 405,000 joules and divide it by the mass, 2,500, divided by 9.8. Again, pull out your calculator, see what you get. And my calculator tells me I'm going to need to raise it approximately 16.5 meters to get that potential energy, which is going to convert into the kinetic energy I need for it to hit the ground at 18 meters per second. Example number 11, this is the last one. A person is running at 7 meters per second. If they have a kinetic energy of 1764 joules, what is their mass in kilograms? So we have kinetic energy given, we have speed given, we're looking for mass. We have Ke equals 1/2 mv squared. Before we start plugging numbers in, we need to rearrange this for mass. So maybe try that on your own, pause your video, and then come back and see if you got it right. So to solve this for mass, again, the first thing I'm going to do is move this 1/2 to the other side by multiplying both sides by 2. So the 1/2 and the 2, they can cancel. So this gives me 2 kinetic energy equals mass times velocity squared. And now to get mass by itself, I'm going to need to divide out this velocity squared because it's multiplying velocity squared. So I'm going to divide by velocity squared and divide by velocity squared on the other side. So that leaves me with mass equals 2 times the kinetic energy divided by velocity squared. Now I can start plugging in my numbers. So I've got 2 times 1764 divided by 7 squared. And again, pull out your calculator, see how you do. And my calculator tells me my person has a mass of 72 kilograms. All right, one more fun video to finish us off. See if you can spot the energy transformations from potential to kinetic in the video, and then we'll be done.
Isn't it nice when things just work?